Hi everybody, this is Ms. Suchi here. We are going to go through geometry lesson 5.6, which is properties of special parallelograms. So you've already talked about parallelograms and how they have opposite sides parallel. Well, there are multiple quadrilaterals that can be considered as parallelograms, even though they have a more specific name. So our objectives today are to be able to discover and apply the properties of any type of parallelogram, whether they are fancy ones like we'll learn today or just a normal parallelogram. All right, here we have a diagram of two rulers crisscrossing each other. Now, when you have a ruler, the edges of that ruler should be straight. If they're not, that's a pretty pathetic ruler. So because they're straight and they're going in the same direction, this figure that I have here is going to have parallel sides that way, as well as parallel sides this way. So technically, that's a parallelogram. So those sides are parallel, and that makes a parallelogram. Now, question 2 says, because these two rulers are the same type of rulers, and they were purchased at the same store, same manufacturer and everything, the distance across the rulers are going to be the same on both rulers, which means the width, when I go across here, is going to be the same for each of these sides. So not only are my sides parallel, but the distance between the parallel lines is equal. And that means all the sides are congruent. Now, because all the sides are congruent, we have a special type of parallelogram. But there is a conjecture that goes along with this, and it's called the double-edged straight edge conjecture. And it basically says what we just saw with the rulers. If we have two parallel lines getting crossed by another pair of parallel lines, and they're the same distance apart, the parallelogram that is formed is called a rhombus. Now we want to make sure that we have specific outline of what a rhombus needs to have in order to be classified as a rhombus. So a rhombus is a quadrilateral. That means it's got four sides with opposite sides that are parallel, and this is the key part here. Opposite sides parallel just means a parallelogram, but to be that special rhombus, it must have four congruent sides, or all sides congruent. So what we can do now is we can take that information and put it in on our picture. So I'm going to just zoom out here so we can see the whole picture. And first thing I'm going to mark is that the opposite sides are parallel. So here is my special rhombus. And to make those opposite sides parallel, I'm going to do those arrows showing that they're going in the same direction. The left and right sides need a different set of arrows showing that direction that they're going in. And then finally, we need to show that all sides are congruent. And that's going to be our hash marks. So I'm going to put the same hash mark in each side on the rhombus. So here we have four congruent sides, two pairs of parallel sides. This is our rhombus. All right, now given this rhombus, it's going to ask us a few questions. So I'm going to zoom in just a little bit here. And first question is, well, if this is a rhombus, we should probably mark it as a rhombus. So I'm going to put in marks that each side is the same length. And then the top and bottom are parallel. And the sides are parallel. Okay, now I see some more details in this rhombus. First of all, the diagonals are drawn in. And so with the diagonals drawn in, it's giving me some measurements that maybe we wouldn't have seen before. So it says, using the length of the diagonals, what would point M be? So if I'm looking at the diagonals, that gets me to point M, and then follow the rest of the diagonal. That gets me all the way across. And those two portions of the diagonal are the exact same length. Now if I look in the other direction to point M and to point M, those ones are also the exact same length. So that means point M is smack in the middle of the diagonals. When it's in the middle of a segment, that is called the midpoint. So what we could also do now is we could add in some hash marks showing that these pieces are the same length and these pieces are the same length. Now this is going to get kind of messy because it's got so many marks. The numbers do tell us that the pieces are the same as well, so you wouldn't have to put the hash marks in. All right. Now, if both diagonals are getting cut through that midpoint, that means they're cutting each other in half, or they are bisecting each other. Now remember, that means half. All right, now it says find triangle AMD. So I'm going to go back up here, AMD. So I'm going to highlight that triangle in another color. Let's try orange. Here is triangle AMD. Okay, let's see what the question says. It says calculate the value of angle M using the triangle sum conjecture, which means the triangle's total angle degrees is 180. Well, right now we have an angle measurement of 25, 65, and angle M, and they have to total 180. So I'm just going to subtract those from the total, and that's going to get me the size of angle M. Now, I'm not super great with math in my head, so I'm going to use my calculator. 180 minus 65 minus 25. I got 90 degrees. What do you know? It's a right angle. So because I saw that that's a 90-degree angle, I'm going to put that little box in the corner showing that that's 90 degrees. Now, because I have the two lines crisscrossing, I could put the 90 degrees here, or here, or here. All four corners are going to be 90 degrees in this case. So going back down to that question, the measure of angle M is 90 degrees. Now, if the two diagonals are crisscrossing at 90 degrees, that means that they are perpendicular from each other. And remember, that means a 90-degree intersection. All right, there is our rhombus. So let's summarize. The diagonals of a rhombus, those were bisecting each other, and they were crossing each other at 90 degrees. So they are perpendicular, and they bisect each other. So that means cut in half. And perpendicular means 90 degrees. Whoops. Okay, now it says, look at the corners A, B, C, and D. What do you notice about those corners? Remember, vertex is a special name for corner. So if I look at corner A, well, 65 and 65. Corner B, 25 and 25. Corner C, 65 and 65. Corner D, 25 and 25. So I'm noticing that the opposite corners are the same size, and the diagonals are cutting all of the corners in half. So we've got opposites are congruent, and they're cut in half. Okay, well, let's make a statement about that. Rhombus angles conjecture. Let's see here. The diagonals of a rhombus bisect the angles of the rhombus. That means they cut them in half. Now, the opposite angles being congruent, that's because it's a property same as a parallelogram. Remember, a rhombus is a parallelogram. It's just a fancier parallelogram. So down here it says, which vertices are the same size? That's the opposite vertices. And if we look at our triangles that are being made, back here on our picture, we have 4 triangles. 1, 2, 3, 4. And those 4 triangles all have the same 3 corners, 65, 25, and 90. And they also have the same 3 matching sides. The outside length, one of the diagonal lengths, and the other diagonal length. So here we have a triangle where all 6 of its parts match the other triangles. So back in our questions here, it says what congruency shortcut would tell us that all 4 triangles are congruent? And in reality, because we have so many parts listed, it could be side, side, side. It could be side, angle, side, angle, or side, angle, angle. All of those, because we have 6 things listed, could be true congruency shortcuts for us. All right. When you have those congruency shortcuts, remember, it means that everything is the same length or everything is the same size because corresponding parts of congruent triangles are congruent. Great. Whew, that was a lot. Okay, what we're going to look at next is yet another parallelogram. This one is more familiar because we've learned about this one since elementary school. This is a rectangle. Now, to be a rectangle, you need 4 sides. You need 4 90-degree angles. You need opposite sides parallel. And you need opposite sides congruent in length. All right, so I'm going to mark all of that information. I've got 9.5 and 9.5, so those ones are going to be the same length. Got 18 and 18. Those ones are the same length. And then it doesn't show it here, but we do have to have perpendicular sides, which means we'd have those 90-degree corners. That is one of the main properties of a rectangle. All right, based on the diagonal measurements, point Q is the blank, and the diagonals are blank in length. So if I look at the diagonals, here is a diagonal going to point Q and continuing to the other corner. Those are both 10 centimeters. If I look in the other direction, Q and to the other corner, 10 centimeters as well. So that's telling me that point Q is in the middle, or it is the midpoint. But not only is it the midpoint, this rectangle has diagonals that are the exact same length. So they are congruent in length. This is different from the rhombus. I'm going to slide back quick and look at our rhombus. Notice our rhombus, because it's getting stretched out kind of in one direction, one of the diagonals is considerably longer than the other. But because a rectangle is nice, straight up and down perpendicular sides, it is very symmetrical. And so the 2 diagonals going across will be equal in length. All right, so here's formally in a conjecture. The diagonals of a conjecture are congruent and they bisect each other. All right, now step 3 says, because this is technically a parallelogram, it means that the opposite sides are parallel. So when we have those opposite sides parallel and the diagonal slicing through, that creates that image that we used a couple chapters back that looked like this, where we had alternate interior angles that are congruent. And so we can go up to our picture and mark out which corners are going to be congruent because of the parallel sides. So I could say that this corner up on the top right here is going to be congruent to this portion down on the bottom left. Those are alternate interior angles. Now, because we have an isosceles triangle here, 10 centimeters and 10 centimeters being the same, this corner is a base angle of this isosceles triangle, and they would be equal. So I'm going to put the same hash marks, and that process can be repeated up here as well. Now, those ones are also alternate interior angles. That's why they are the same too. All right, now I can do the same thing if I were to flip it around and look at the other parallel sides, the 18s. Here I have another alternate interior angle set, that is congruent. And again, because we have isosceles triangles, these two base angles will also be the same. All right, so we marked in the alternate interior angles that are congruent. Okay, now we're going to do some practice looking at the properties of rhombuses. So remember, on a rhombus, it's got 4 congruent sides. The opposite angles are congruent, and they get bisected by the diagonal. The diagonals meet at 90 degrees, or they are perpendicular. So using those properties, here we can see ED is a length of 12.6. If this is in fact a rhombus, the opposite side should also be 12.6. All right, over here, I've got a rhombus again, which means all 4 sides are the same length. Well, if that's true, we have an isosceles triangle. And so angles 4 and 2 will be the same. And because the opposite corners are also congruent, 1 and 3 will also be the same as 2 and 4. So there's a couple different ways you can go about this. I like using the fact that a triangle adds up to 180. So I would take 180, subtract off the 73, and get whatever's left over. I'm going to need my calculator. 180 minus 73. Okay, well that gives me 107. Okay, now I've got 2 angles left over, and I know those 2 angles are going to be the same. So I need to split that 107 in half. Ugh. So divided by 2, I get 53.5. So that means angle 1, angle 2, angle 3, and angle 4 are all 53.5 degrees. All right, doesn't really have an order here to go, so I'm just going to go on the left one. Again, we have another rhombus, practicing with rhombuses. So that means all 4 sides are the same. So I have that same special isosceles triangle again. So we can repeat this process to find angle 3. So I'm going to start with 180 for this particular triangle. Let me highlight it for us. I'm going to subtract off the 106. Ugh, let me do that in my calculator here. I get 74 left over. And then I need to split that between the 2 angles. So divide that by 2. Divided by 2, I get 37 degrees. So that means angle 3 is 37 degrees. This angle here, oops, I wrote that backwards. 37 degrees. And their mirror image, because remember it's symmetrical, this would be 37 degrees and 37 degrees. Now I only have angle 1 left. And opposite corners in a rhombus are congruent. So this is 106 degrees. All right, I'm gonna erase some of this just so I have some room to work with. Here we go. This next rhombus, remember we're working with rhombuses in this case. We've got both diagonals drawn in, so right away I know that they are perpendicular. They're crossing at 90 degrees. So all of these corners right here in this middle are 90 degrees. Now that makes me have a really nice right triangle. So I can figure out this missing corner down here. And remember, all 4 of these triangles are going to be congruent because those corresponding parts match up in a certain order that lets us say, yes, the triangles are congruent. So I'm going to take my calculator again, and I'm going to start with 180, subtract off the 90, subtract off the 52, and see how much I have left over. All right. Oops. 180 minus 90 minus 52. You get 38 degrees left over. So that's this corner right here. Now remember, the diagonals bisect the angles of a rhombus. So angle 3 is also 38. And the opposite corners are always the same. So angle 1 is also 38. and that angle next to it is 38. Okay, now because opposite corners are the same, I could use that property to find angle 4 as well. 52 folded over, that would be angle 4. And we could also put those 52s in this corner as well. Whew, all right. I would really love for you to try the last rhombus all on your own, and then check your answer to see if you got it right. All right, here's the answer. Angle 1 is meeting where all of the diagonals crisscross on a rhombus. They are perpendicular, so those are all 90 degrees. Using that opposite angles are the same, this 25 would repeat over here. Knowing that the angles get bisected, the 25 would repeat where the diagonal is getting cut. So this one, angle 4, is also 25 degrees. And then finally, we have a triangle. Actually, we have 4 triangles, but each triangle has to add up to 180 degrees. If I subtract off the 90 and the 25, let me get my calculator. Oh, that leaves me with 65 degrees in that triangle. So here I have a 65-degree angle. Angle 3 would also be 65. Angle 2 would also be 65. And this other corner would also be 65. Great, that's our rhombus practice. All right, now for some practice with rectangles. So remember, on a rectangle, you have to have 90-degree corners. Well, D and B are already showing as 90. But remember, angle Y, or I guess this whole corner, angle C. I think angle Y is just that little piece. And this corner, angle A, those will also be 90. So because angle A already has part of the angle listed, I can say 90 minus 65, which will get me the rest of that angle, or portion X. Okay, let's do some math here. 10 minus 5 is 5. 8 minus 6 is 2. So I got 25 degrees here. Okay, now there's a couple different ways you can solve this problem. We can look at the triangle, and we can say, well, because it's a triangle, it has to total 180 degrees. 180 minus 90 minus 25, I'm back to 65 degrees. But that's also because of the alternate interior angles being congruent. That's because this is a parallelogram and the opposite sides are parallel. So if that's the case, I could also write the 25 down in this corner here. Okay, next question. This one says, S to A is a length of 5. What is the length from R to T? Because we are working with rectangles, they are symmetrical. We could fold them right down the middle, everything would match up the same length. So that means RT's length is also going to be a length of 5. All right, last rectangle question here. It says N to L is a length of 26. So we could also say that M to O is a length of 26. And then because of these side lengths, I could say that MN is also a length of 24, and NO is also a length of 10. Great. Let's look at one more special parallelogram. This one is a square. Again, very common from all of your years in elementary school, playing with shapes and blocks and things when you were little. But to be a square, you have to have 4 right angles and 4 equal sides. Now, if we also look at the square here, we've got some other measurements that are going to give us some helpful hints on other properties. Because this is a parallelogram, that does also mean that the opposite sides are parallel. We just don't have to show it because of the 90-degree symbols. Those ones are automatically telling us that the top and bottom have to be going in the same direction. They're both coming off of that side, KN, at 90 degrees. All right, based on the diagonal measurements, point J is the what, and the diagonals are what in length. So this is kind of a common theme here. Point J, well, that's right in the middle. All of those happen to be the same length. Whoops, let me add another hash mark so that it's different than my outside length. So I've got 8.8, 8.8, 8.8, 8.8. That would make this the midpoint. And the two diagonals are totally congruent in length. So that's pretty much the same as what we noticed with our rectangle, where the diagonals were the same in length, and we were getting it cut in half. But on the rectangle, the corners were not always getting cut in half. However, on the square, the diagonals are more similar. So just like on the rhombus, the diagonals intersect at each other at a 90-degree corner. This means that they're perpendicular. We also have those four triangles being split up, and because of these lengths being the same, we have four isosceles triangles. Now, because of the 90-degree here, they are right isosceles triangles, which means each of these individual angles has to be 45 degrees. So just like in the rhombus, the diagonals are also bisecting the corner of the square. Whoops. So these are right isosceles triangles. All right, now because they're right isosceles triangles, I took that 180, subtracted off the 90, and got 90 left over. But then we had to split it for those two base angles. That's where I came up with the 45 degrees. So that means the diagonals are the bisector of each vertex angle on the square. All right, here we go. Official conjecture. The diagonals of a square are congruent, bisect each other, and I guess I should say perpendicular bisectors of each other, and they bisect the corners on the square. All right, here is a square example. We are going to mark down everything that we can based on this example here. So we have a 16 centimeter side. That means all sides would have to be 16 centimeters in order to be a square. We have part of a diagonal as 11.3. Diagonals get bisected, so this is also 11.3 centimeters, and the two diagonals are the same length. So, oops, this one would also be 11.3 and 11.3. Now, because the diagonals are perpendicular bisectors, we have 90-degree corners happening right where the diagonals bisect each other. And then finally, because of this right isosceles triangle, each of these corners, which total 90, are getting split in half to be 45 degrees. Excellent. All right, here is our summary that we will complete later on. Thanks, everybody.